Hey everyone, welcome back to Data Elevate Hub, your one-stop destination for learning all things in data roles. In today's video, we will dive deeper into the roadmap to become a data engineer, a step-by-step journey that transforms raw data into a meaningful insights. Let's imagine you are running a business where all your sales data, application logs, and inventory details are stored in a database. Now you need to analyze your inventory and create a report to share with the manufacturing providers. Sounds straightforward, right? But here is the catch. Without the right tools and knowledge, this task can quickly become overwhelming. Let's start with the foundation skills of data engineering. Python. And why do we need Python? Python is a versatile beginner-friendly programming language. It provides libraries and frameworks for data manipulation, data analysis, and data engineering. It serves as the backbone of data workflows, and it's your best friend in your data. Let's first focus on the basic concepts. Learn the building blocks of Python, including syntax, variables, and data types. These basics enable you to write your first lines of code and understand how Python is working. Next, data structures. Master in lists, dictionaries, tuples, and sets to store and manage the data efficiently. So these structures are essential for organizing the data in pipelines and real-world applications. Next, control flows. Use if-else statements, loops, and conditionals to control your logic of your program. So these tools helps to automate the decision-making process in your scripts. And next, functions. Writing reusable blocks of code to simplify tasks and improve the maintainability. Functions make your code modular, clear, and scalable for larger projects. Next, having an understanding of basic OOPS concepts is important. Learning object-oriented programming principles like classes, objects, inheritance, polymorphism, abstraction, and encapsulation. So these concepts are vital for creating complex and reusable systems in the Python applications. Now let's discuss about the key important libraries in Python. So pandas. While plain Python can handle data using lists and dictionaries, but pandas provides a more efficient and convenient way to handle the larger data sets with its data frame structure. And it offers built-in methods for data manipulation, cleaning, and data analysis that would be very helpful. Otherwise, it requires a lot of custom code to analyze the data. Next, NumPy. So Python lists are not optimized for numerical computations or larger data sets. So here NumPy provides a highly efficient array operations and mathematical functions and significantly improving the performance when handling the numerical data and performing the calculations on large arrays or matrices. Next, Matplotlib. In plain Python, plotting data involves writing custom code to visualize the graphs, which can be very difficult. So here Matplotlib provides a simple and efficient way to create high quality plots and visualizations. So it saves our time and making it easy to represent the complex data in graphical form. Let's think about it. How impactful if you show the monthly sales trend in a bar chart visual instead of tabular report. It is easy to understand. And next, SQL. SQL is structured query language. And why do we need SQL? So it is the universal language for interacting with the databases. It allows you to query, insert, update, and delete the data efficiently. Now let's take a scenario of customer order tracking system. Imagine you need to track all customer orders placed on your platform to improve the delivery operations. So the orders data is stored in a relational database like MySQL or PostgreSQL. And you can use the SQL to fetch the customer orders based on their customer IDs or dates. And you can use the SQL queries to analyze the data. So for example, to calculate the orders trends or delays in the orders. And now let's discuss about the basic concepts in SQL. So first one is DDL, data definition language. It provides the SQL commands to create the table or to delete a table or to modify a table. It's all about the table definition level, not inside the table data. So next we have the DML, data manipulation language. So here all these commands are useful to modify the data which are already present or which you want to insert or you want to delete. And data query language. So these commands are helpful to fetch the data from the database table. And next we have where class. If you want to filter out the data based on a condition, you can use where class. And the joins are helpful to combine the data from multiple tables. And string functions, for example, if you are having a single string column, so you want to convert the string column, all the values in the string column, to uppercase. So now you can use the upper function, and you can use the lower function to, in the similar way, you can convert into lowercase, or you can use the concat to combine the two string columns. These are some of the string functions, and there are many more. In the similar way, we have aggregation functions. So these aggregation functions are used to calculate the total sum, or a total count, or total average, and minimum value and maximum value on top of the data. And the next, subqueries. So subqueries helps us to use the query inside another query. For example, you have a query and you want to use the query output for the another query. So in that case, we can use the subqueries. And next, advanced concepts. So first one is CTEs, common table expressions. So we already discussed about subqueries, right? So we are using one query inside another query. So if you want to use that inside query in multiple places of different queries, so in that case, defining the query inside the all the queries is not a good practice. So we can define one common table expression. So here we will write the whatever the inside query required, and we can use the name wherever we want to use that query. So it helps us to minimize the complexities. And next, pivoting. So pivoting is to transform the rows into columns and performing the aggregations. And next, analytical functions. So these analytical functions are very important. So if you want to apply the aggregations on top of particular window, for example, department level sum you need, so you have to perform the aggregation on top of the department itself, and you want to perform particular range. So these analytical functions helps us to calculate the cumulative sums, moving average. These are some of the analytical functions. And why Python and SQL are work together? Here Python is for scripting and data transformation and data visualization, and SQL is for querying and storing the data efficiently. So for example, using Python to write a SQL queries dynamically, and we can analyze the results using the Python. And next section is DBMS and data warehousing. So DBMS, database management system. So here a database management system is a software that organizes, stores, retrieves and manages the data efficiently in structured formats. So it ensures data is easily accessible and maintains data consistency, integrity and security. Now, why do we need DBMS? It helps to organize the raw data into a meaningful tables, and it connects the related data sets using primary keys and foreign keys. It will establish the relationships, and it avoids the duplication through the normalization process. So it maintains the data consistency, and it provides the tools like SQL to retrieve, update, manipulate the data efficiency. So it is easily accessible. And now discuss about the core concepts in DBMS. Normalization. So normalization is the process of splitting large and unorganized table into a smaller and logical ones to reduce the redundancy. For example, splitting a customer table into separate tables for customer info and order details. And next, entities and relationships. So here entities are the objects in the database. For example, earlier we splitted the customer table into customer info and order details. So here customer is a entity and order details is a entity. Now what is the relationship? So here the connectionship between the two entities is a relationship. So for example, customer places an order. And next, ACID properties. So ACID means atomicity, consistency, isolation and durability. So atomicity tells us that transactions are completed entirely or not at all. If the transaction is failed in the middle, so the entire transaction is cancelled. And next, consistency. So it ensures the database remains in a valid state after a transactions. And isolation. It prevents the interface between the multiple simultaneous transactions. And next, durability. Ensures data remains saved even after the system is failed. And the next important concept is indexes. So it helps us to improve the query performance by creating the shortcuts to the data, like an index in a book. Now let's take a example scenario for DBMS. For a food delivery app, how the DBMS organizes the data. So it stores the customer details into a customer table and the records of orders placed by the customers into a orders table, and restaurants table, it contains the restaurant information. So here is the relationship is a customer places an order at a restaurant. This structure allows you to query all orders placed by a specific customer and retrieves the most popular restaurants based on the orders. Next, data warehousing. A data warehouse is a large centralized repository of data designed for reporting and analysis. So it integrates the data from multiple sources, making it ready for business intelligence tools to derive the insights. And why do we need data warehousing? Data consolidation first. So it combines the data from the different systems into one source of truth. And next, historical analysis. It stores the historical data for a long-term trend analysis, and it enables the efficient reporting and data in visualization. So it's for improved decision making, and it is optimized for queries. Unlike DBMS, it depends on heavy read operations like BI reporting. And next, core concepts in data warehousing. ETL, extracting, transforming, and loading. So here extract means collect the raw data from the multiple sources like CRM source, DBMS, social media, and transform and clean and convert the raw data into a usable format. Load, and the transformed data has been loaded into the warehouse. And the schemas, it uses the star schema, snowflake schema. A star schema, a simple design with one fact table connected to the multiple dimension table. For example, sales data is connected to products and the customer dimensions. And next, snowflake schema, a more complex design where dimensions are normalized. And next, OLAP, online analytical processing. It allows us to slicing, dicing, and drilling down into data for analysis. And for example, analyzing the sales by region, product category, and time period. Data marts. These are the subsets of the data warehouse focusing on the specific business area. For example, like marketing, finance, HR. Now let's take a data warehousing scenario. For a retail company, a data warehouse consolidates sales data from the stores and online platforms, and customer demographics from CRM tools, and product inventory data from warehouses. And business intelligence tools use this data to generate the dashboards showing the regional sales trends and predict the inventory shortages during the peak seasons. And now section 3, big data and processing concepts. So what is big data? A big data refers to a large and complex data sets that cannot be effectively managed, processed, or analyzed by using the traditional tools. It is characterized by volume, velocity, and variety. So here volume refers to the huge size of data, example terabytes, petabytes, and velocity. It is the speed at which the data is generated, example real time streaming. And variety, so variety refers to the formats of data, like example structured, semi structured, unstructured data. Why do we need big data processing? Scale. Traditional systems can't handle the massive amounts of data. Based on the load, big data processing tools can scale up the resources. Next, insights. So here we can extract the actionable insights from the complex data sets, because it allows us the distributed processing. And real-time analytics, process the data as it generated and enabled for the quick decision making. And for efficiency, it handles the diverse data formats like text, images, or videos seamlessly. Next, core concepts of big data processing. So, distributed storage and processing. So the data is stored and processed across the multiple machines instead of a single server. Like in Python, Pandas, so we are processing it in a single server. So if the data size is huge, the single server can't handle that much data. So here, so big data can allows us to process the data in multiple servers. So systems like Hadoop and Spark split the data into chunks and they distribute them for parallel processing. So it improves the performance and fault tolerance. Next, MapReduce framework. It is a programming model that processes the data in two steps. So first one is map. Here is the process for individual chunks of data in parallel, and reduce. Here it will aggregate the outputs of the map tasks. Let's take an example. you want to count the number of occurrences of each word in a larger text data set. So here the map task will process the each document and counts the words locally, and the reduce task will take the aggregate results into the final result. And next, batch and real-time processing. So here batch processing allows us to process the large volumes of data in chunks over a time, let's say overnight or daily jobs. So here the for example tool is Hadoop. And for real-time processing, it's a process of streaming data in near real time. So tools are Apache Kafka or Apache Spark streaming. And data formats in big data. So structured data, semi-structured data, and unstructured data. So we have to know about all these concepts. Now let's talk about big data processing tools. First one is Hadoop ecosystem. So it consists of HDFS. HDFS means Hadoop Distributed File System. It is a distributed storage for the big data. And next we have a processing engine, MapReduce for parallel processing. And next ARN. It is a resource manager to perform the processing. So next we have Apache Hive. So Apache Hive is a data warehousing and SQL like query language, and it is built on top of the Hadoop ecosystem. It provides an abstraction layer for interacting with the Hadoop's HDFS, Hadoop Distributed File System. So using like simpler SQL queries, making it easier for developers and analysts to work with the larger data sets without needing to learn complex MapReduce programming or any other low-level Hadoop components. And next, Apache Spark. So why Spark is better? So here Spark is faster than MapReduce due to in-memory processing, and it is almost 100 times faster than the Hadoop because it runs in RAM. So the features of the Spark are it supports batch processing, stream processing, and interactive data processing, and it offers libraries for machine learning and graph processing. Next, Apache Kafka. It handles the high throughput and real-time data pipeline. It majorly it used as a messaging system to move the messages from the source to target, and it can allow us to process the data in real time. Next, NoSQL database. So handling the unstructured data and semi-structured data better than the traditional SQL databases. So for example, we can store the storing and querying the social media posts. Example tools are MongoDB, Cassandra. Now let's talk about some big data processing scenarios. Let's take a use case, real-time fraud detection in banking. So a bank processes millions of transactions daily and wants to detect the fraudulent transactions in real time. So here the challenges are it's a real-time data, so many transactions are happening, so high volume of transactions and high velocity due to real-time processing and high variety in transaction processing, transaction formats and logs. So here the solution is we can collect the real-time data using Kafka, and it will stream the data into the HDFS for the batch processing and in NoSQL for real-time processing. And we can process it using the Spark streaming to analyze the transaction data in real time, and we can flag the potentially fraudulent transactions within a milliseconds. And next we have the most important concept, Apache Spark. It is very fast, flexible, and unified data processing. Now, what is Apache Spark? So here Apache Spark is an open source distributed data processing engine, and it is designed for big data applications. It is known for its speed and in-memory capabilities and support for wide variety of data processing tasks such as batch processing, streaming, machine learning, and graph computations. Why do we need Apache Spark? So it processes the data faster than the traditional MapReduce due to in-memory computation, and it handles the terabytes or petabytes of data by distributing it across the clusters. And it supports multiple workloads, batch streaming, machine learning, and graph processing on a single platform. And it has high level APIs in Python, Scala, Java, and R language. And it is fault tolerant. It will automatically recover from the node failures during the processing. And core concepts of Apache Spark, RDDs, resiliently distributed data sets. So it is immutable, the distributed collection of objects stored across the cluster. It provides the fault tolerance and parallel processing capabilities. Next, data frames and data sets. A data frame is a tabular data structure similar to a SQL table. And data set is a strongly typed API for working with the structured data. This simplifies the operations and optimizes performance. And next, Spark core components. So first one is Spark core. It handles the basic functionalities like task scheduling and memory management. Spark SQL. It provides the SQL-like querying on a structured data. Spark streaming. It processes the real-time data streams. And MLlib, a library for machine learning tasks. And GraphX, a graph computations and analytics. And now let's take an example scenario for Apache Spark. So one is real-time log processing. Now let's take a Spark use case scenario of real-time log processing. So here the problem is a company wants to monitor the server logs in real time to detect the anomalies. So here the solution is we can use the Kafka to stream the logs into Spark streaming and the filter the logs for error patterns using the Spark, and we can trigger the alerts immediately when anomalies are detected. And the another scenario is using machine learning for fraud detection. So here the problem is to identify the fraudulent credit card transactions. How we can solve this problem? So first we can data pre-processing using Spark SQL to clean and prepare the transactions data, and we can train the model using the Spark MLlib and score the transactions in real time using the Spark streaming and catch the fraud as it happens. Advantages of Apache Spark. So it's in-memory processing. It speed up the data processing by keeping the data in memory rather than reading or writing into the disk. And distributed computing scales out to handle large data sets efficiently. And flexibility. It supports a wide range of languages, Python, Scala, Java, and R. And unified engine handles all type of transactions like processing, batch, streaming, and beyond. And next we have cloud computing for data engineering. So what is cloud computing? So it is the on-demand delivery of IT resources such as storage, processing power, and databases over the internet, eliminating the need of on-premises infrastructure. And why cloud is essential for data engineering? So it has scalability, easily handle the fluctuating workloads. Based on the workload, it will scale up or scale down. Cost efficiency, so we have to pay only whatever we have used. And availability, we can access the resources at any time and anywhere. Flexibility, choose from a variety of services like storage, processing, and offering the AI tools. And it's a managed service, so we have to focus on development, and while the cloud provider handles the infrastructure upgrades and all these things. And next, key cloud platforms: Azure, AWS, and GCP. So we have covered an incredible amount of knowledge today: tools, techniques, and concepts that are essential to mastering data engineering. From understanding power of Python and SQL to diving into big data processing frameworks like Apache Spark and utilizing the cloud platforms for scalable solutions. You have now clear roadmap to become a data engineering expert. Let me tell you why this is important. Data engineering is the backbone of every modern business. Companies rely on us to handle vast amounts of data, to organize it, to process it, and to turn it into actionable insights. When you master these skills, you don't just become a data engineer, you become a key player in driving the insights and success. Learning all of this might seem overwhelming, but that's why I have designed this channel for you. My goal is to simplify these concepts, breaking them into step by step lessons, and teach them in a way that feels approachable and exciting. No matter where you are in your journey, whether you are a beginner or a transitioning into data engineering, this channel will guide you every step of the way. So what can you expect here on Data Elevate Hub? Structured learning starting with the foundations, Python, SQL, and DBMS, and hands-on practice with real-world scenarios that make learning meaningful, and advanced concepts like big data processing, Apache Spark, and cloud platforms explained in a simple way, and plenty of tips and tricks to help you to stand out in interviews on the job. If you are serious about becoming a data engineer, this is place to be. Hit the subscribe button now and start building the career you have always dreamed of it. Like this video if it's been helpful, and leave a comment with your questions or suggestions for future topics. And don't forget to check out our upcoming videos where we will continue this exciting journey step by step. Remember, every great data engineer started somewhere, and this could be your starting point. Let's learn together, grow together, and elevate your career in data. See you in the next video.